Okay, we are on. Today you are going to learn Chapter 8, part of it, not all of it. We actually already did Section 8.2 when we studied the electron configurations for ions. So we're going to skip that in this lesson. So 8.1, we will start with that one. How did the periodic table come to be? Well, it wasn't until the mid-1800s that the current periodic table as we know it came around. And it was developed or derived by Mendeleev in the 1870s. The first rendition, the periodic table was arranged by atomic masses only, and then Mendeleev came along and noticed some interesting periodic properties of the elements, hence the word periodic table. Mendeleev looked at chemical properties along with atomic masses, and the periodic table that he came up with is extremely close to what we see today. That's it for Section 8.1. On to 8.2, which we already did, so we're moving on to 8.3. That was really fast, wasn't it? 8.3 is going to take quite a while, especially when I keep clicking on things that I shouldn't click on. So here we go. 8.3, periodic variation in physical properties. So this periodic table is called the periodic table because we see patterns that happen in a periodic way throughout the periodic table. In fact, these trends occur along a row of the periodic table, so we call each row a period of the periodic table. Very interesting, isn't it? And a period just means something that repeats itself over and over. So one periodic property is effective nuclear charge, otherwise known as zeff, Z effective. And Z effective is Z minus sigma. What in the world are Z and sigma? I already told you what Z effective is. And I seem to have lost my recorder. I want to pause. All right, so sigma, this symbol right here, is called a shielding constant. It's how much positive nuclear charge is shielding by electrons in an atom. And Z, you've seen this before, you may not remember. Z is the total number of protons in an element. So Z is also the nuclear charge with no shielding, because the number of protons is the total charge if no shielding were to occur. The second thing we're going to look at that has a periodic variation is the atomic radius. And along a period of the periodic table, atomic radius decreases as you go across the periodic table, and it increases as you go down the periodic table. You don't need to write that down because we're going to have a whole section on that later on. Atomic radius is defined as half the distance between two nuclei and two neighboring atoms. The last thing we are going to look at today is ionization energy. That's Section 8.4. It's not actually in 8.3, but since we're just talking about what periodic things we're going to look at today, I wanted to include ionization energy in the introduction. And this is defined as the energy required to remove an electron from a gaseous atom or ion in its ground state. Ground state is just how we learn to do electron configurations. If there's something different about it, it's either an impossible configuration or an excited state configuration. Moving on, what is this effective nuclear charge stuff? Z effective. So I have some data that I got from the internet on effective nuclear charge. And reading this can be a little bit confusing. So you want to make sure you actually know how to read this chart. Okay, so we have all the elements, hydrogen, lithium, beryllium. Underneath each element is the number of protons, or Z, for each element. So if we look over at fluorine over here, fluorine has 9 protons. Now, we've got this 1s, 2s, 2p. Those are the actual electrons, and then the number that you see in the row of a 2s or a 2p is the charge felt by the electrons, or by the electrons. So for instance, this one would be the charge felt by the 2s electrons. This right here would be, notice that's in the row of a 2p, that's the charge felt by borons 2p electrons. So in each row we have specific types of electrons, and the numbers in here are the charges felt by that type of electron. And you should notice a general trend here that as we go up this is kind of like a periodic table, it's not the entire periodic table, but as we go up a periodic table, do you notice that the effective nuclear charge, Z effective, it decreases? Here we have 3.5, 2.5, 1.31. So Z effective decreases as we go up the periodic table. As we go to the right in the periodic table, we see a general increase in Z effective. So if we're at gallium and we're looking at our 4p electrons, 6, 6.7, 7.4, 8.2, increase in the effective nuclear charge as we go to the right in the periodic table. That's because we're getting more protons. Now, one of the things that confuses students is when you go down the periodic table, notice potassium has 19 protons. And its effective charge that those 4s outer electrons are feeling is only 3.5, even though you have 19 protons. Many students think, well, why is that? That just seems really strange. But it actually makes sense when you think about inner core electrons versus the outer electrons. So I'm going to draw potassium. No, I'm not. Now I'm going to draw a potassium atom. So we've got our 19 protons right in the middle for potassium. And let's see, potassium is 1s2. So in the first shell, we have 2 electrons. And then we have 2s2, 2p6. In the second shell of potassium, shell 2, we have 8 electrons. And in the third shell for potassium, we have 3s2, 3p6. Oh, I'm going to have to draw one more circle here. In my third shell, I also have 8 electrons. And then in my fourth shell, shell 4, I have only 2 electrons. This is for potassium. This is a model of potassium here. Now, here's the tricky part. These 2 electrons in the fourth shell, our outer electrons, they've got 8 plus 8 plus 2. Altogether, they've got 18 electrons between them and the nucleus. Wait a second, something's wrong. There's only 1 electron here for potassium, not 2. Potassium has only 1 electron in the 4s sublevel. Sorry about that. Okay, so we have 18 electrons between this 4s electron and the nucleus. Now, these 18 electrons are going to shield part of the positive charge of the nucleus because these are all negative. These electrons, they're all negatively charged. So instead of feeling that plus 19 from potassium, this 4s electron is only feeling 3.5, a charge of about 3.5. So the electrons, these inner core electrons here, they're not fully shielding one-on-one, 1 electron to 1 proton, because if they did, that outer electron would feel 19 protons minus 18 electrons. It would only feel a charge of 1, but that 4s electron actually feels a charge of about 3.5. So hopefully this is making some sense. It can be a little confusing, and we'll go over it a little more. By the way, you will not ever have to memorize this chart. No expectation of that sort whatsoever. But I put a question up here. What charge do krypton's 4p electrons feel from the nucleus? You might want to pause, look up this chart, want to make sure you're reading the chart correctly. I'm about to show you the answer, so pause if you want to do it on your own, and here's the answer. this 9.338. So we have krypton. The 4p electrons of krypton feel a charge of 9.338. Okay, another one. What charge do krypton's 4s electrons feel from the nucleus? Let's see if you can read this correctly. So pause. I'm going to put up the answer in a moment. And here we go. So we go to the 4s electrons and we go over to krypton and we see krypton's 4s electrons feel 11.316. So the s electrons are feeling a little bit more of a charge than the p electrons. And notice those d electrons feel a much larger charge because those d electrons are closer to the nucleus than the 4s or the 4p electrons. Those 3 d electrons are in the inner core for that atom. Okay, so why does the Z effective for the outer electrons of krypton not equal 36 when there are 36 protons in krypton? So I just went through the example with potassium. So let's see. I'm going to give you the reasoning in a moment. But think about it. Why does Z effective for the outer electrons of krypton, those 4p electrons and or the 4s electrons, why do those electrons, why does the charge not equal 36 when krypton has 36 protons? Shouldn't they feel all 36 protons? Why don't they? Well, here's the answer. Pause again if you want to think about it. So, here we go. Krypton has a whole bunch of electrons in the first, second, and third shells. And those 28 electrons that are in those first, second, and third shells shield the 4s and the 4p electrons from the charge of the protons in the nucleus. Thus, instead of feeling this plus 36, the 4s feels only 11.3-ish, and the 4p feels only 9.3-ish. You don't have to memorize any of these numbers. You do have to know the general trend. You have to understand that as we go to the right in the periodic table, we get more protons, and thus the effective nuclear charge increases. And we actually don't at all worry about the effective nuclear charge going up and down on the periodic table so much because you don't need to worry about that. It's a good thing to know that, in fact, when you go up, the nuclear charge, the effective nuclear charge does decrease, but again, it's not as important as this piece right here. This is the really important one, left to right. We have more protons, so the effective nuclear charge increases. Okay, moving on. We are now going to look at the trends for atomic radius. So I've given you this chart, and it shows you the trends. As you go to the right, the atomic radius decreases for the elements, and you can actually see these different radii. And also down here we have, this is the radii of the elements in picometers, or picometers, 10 to the minus 12 meters. And left to right, hopefully you can see, indeed, the radius does decrease. Looks like there's some exceptions right in here, but we're not going to worry about that little exception there. And as we go down the periodic table, the atomic radius also increases, decreases to the right, increases going down. So, any ideas why that might happen? Going down the periodic table should make a lot of sense. It's going to the right that usually confuses students. So let's look at some reasons. Now, as you go to the right on the periodic table, what is happening there? We're getting more protons, higher Z effective. And so what? It's like, what's the big deal? Well, if Z effective increases, the electrons are going to be pulled toward the nucleus. Those outer electrons are pulled toward the nucleus, and that makes the radius smaller. I hope that makes sense. So even though you are getting more electrons, most students think as you go to the right on the periodic table, you're getting more electrons, so the atom should get bigger. But in fact, that's not what happens. The radius gets smaller as you go to the right, and it's because we have more protons. Z effective is increasing. The electrons are pulled in toward the nucleus, and that makes the radius decrease. What about going down the periodic table? What's happening with the electrons when we move down the periodic table? What are we getting more of? You can try to guess. We're getting more shells of electrons. If you have another shell of electron, you're going to be bigger. 4 shells is bigger than 3 shells, is bigger than 2 shells. Remember little babushka-dells. Okay. So those are the reasons for the periodic trends. For atomic radius. Now we're going to look at ionic radius. It's a little more complicated. So it's not complicated if you're comparing ions with the same charge. So if you're comparing Cl1 minus and F1 minus, that trend would be the same as if we were comparing Cl and F. However, ions are complicated. What if we have different charges? So suppose we have 2 ions that are isoelectronic. Which one is going to be a bigger ion or a smaller ion? The one with more protons is going to be smaller. And here's the reason. More protons pull the electrons closer to the nucleus. Okay. There's still some more complicated issues. What about an atom and its ion? S versus S2 minus, Na versus Na1 plus. And here we go. The cation will be smaller than the atom. The anion will be larger than the atom. I do not want you to memorize all of this. I want you to be able to logic through it all. All of this, everything in periodic trends is very logical, and it's just testing your if-then abilities and making sense of the physical sense that protons are positive, electrons are negative, electrons repel one another, protons attract electrons. It's all important. So, these ions. Why is it that the negative ion is bigger than the atom, but the positive ion is smaller than the atom? It's just about losing versus gaining electrons. If you want to keep thinking, you can, and pause, but I'm going to show it to you. So, sulfur versus sulfur 2 minus. They have the same number of protons, but S2 minus has more electrons. So if you have the same number of protons, but one has more electrons is going to be bigger than less electrons. Same reasoning with Na and Na1 plus. They have the same number of protons, but Na1 plus has one less electron, so Na plus is smaller. Pretty simple. I'm noticing that this thing says 17 minutes. I must have forgotten to turn it off at some point, and I hope that if I did, that you fast forwarded through that. Okay, so practice problems. Which has a larger radius and why? If you want to pause right now, you can. Otherwise, I'm about to show you the answer. We're going to look at S versus O. You find where these are on the periodic table, and you look where they are in comparison to one another, and you should notice S, they're in the same column. These two elements are in the same column, but S has 3 shells of electron, O only has 2 shells of electrons. So S is bigger than O. Plain and simple. Sulfur versus phosphorus. So you want to identify where these are on the periodic table, and you can pause if you want. I'm about to put up the answer. So P has a larger radius. These two elements are in the same row, so they have the same number of shells of electrons. But P has one less proton, and if you have less protons, you have a smaller effective nuclear charge, Z effective. So that means phosphorus's nucleus has a weaker pull on the outer electrons, so phosphorus is going to be a bigger atom. All right, P versus P3 minus. We're going through all the different types of problems that we had for ions and atoms now. So you want to think logically, P versus P3 minus. When you have an ion present, you want to compare the number of protons and the number of electrons. So these have the same number of protons, but P3 minus has extra electrons. So P3 minus is bigger. Okay, and again, you can pause after each of these. If you want to think about this yourself, you can pause right now. Think about protons and electrons. So these have the same number of protons. Mg2 plus has fewer electrons, so Mg is bigger in radius. Next one, O2 minus versus F1 minus. So this time, again, when you have ions, you compare the number of protons and the number of electrons. So you should recognize these have the same number of electrons. They're isoelectronic, but one has more protons than the other. Again, pause if you want, and here we go. Here's the answer. So O2 minus has a larger radius. These have the same number of electrons, but O has fewer protons. It has a weaker pull on the electrons, so O2 minus is a larger ion. All right, you're going to do these on your own, and I will show you the answers in a moment. So pause. I'm going to pause myself and put the answers up in just a moment. You don't have to explain the why. Okay, by the way, if you got these all backwards, I switched it up on you to make sure you were actually reading. I wanted to know which has a smaller radius. In our practice problems we were doing, which has a larger radius. So you want to be very careful in these problems, whether I'm asking for smaller versus larger. Now, on to ionization energy, section 8.4. We had this in the intro, but you really have to know these definitions, so I keep rewriting them. So ionization energy is the energy needed to remove an electron from a gaseous atom or ion in its ground state. And here's some data on ionization energy. And ignore the red numbers. Those are melting points. So there are also trends in melting points, but we're not going to worry about those. We are looking at these numbers down here. This is how many kilojoules it takes to remove 1 mole, or to remove 1 electron from a mole of each particular atom. And if you look at these numbers, you'll notice as you go up the periodic table, ionization energy increases. As you go to the right on the periodic table, the general trend is that ionization energy also increases. Why? Why does this happen? What's the reason? Maybe you can come up with it yourself. In case you can't, I have given you the reasons, but if you want to pause and think about it, you can go ahead. But here we go. Now, as you move to the right on the periodic table, you're getting more protons. So Z effective is increasing. If you have a bigger Z effective, you have a stronger force holding the electrons, and it takes more energy to remove the electron. Now what I said is a little bit different from the wording in here. This wording is fine. What I said is fine. However you want to explain it that makes sense to you. You just need to know as you gain more protons in the same shell, so the atoms have to have the same number of shells of electrons. As you gain more protons, you have a higher Z effective, stronger force holding the electrons, higher ionization energy, more energy needed to remove it, and the outer electron. Now what about going down the periodic table? What's the big thing that's going on? We're getting more shells. So as you move down the periodic table, the next element has an additional shell. The outer electrons are farther from the nucleus. And think about it, if something is farther from a nucleus, negatives will be held with less force the farther away they are from a positive area. So the nucleus is positive. If we're comparing an electron that's close to the nucleus versus an electron that's far from a nucleus, the farther electron is not held as tightly. Thus, less energy is needed to remove an outer electron if it's farther from the nucleus. So as we go down the periodic table, down, ionization energy increases because there's more shells and the electrons are farther from the nucleus. Or if we go up the periodic table, ionization energy increases because we have more shells of fewer shells of electrons. Those outer electrons are closer to the nucleus and held with more force. So let's do some practice problems. Wow, we're at 24 minutes. Sorry. Okay, which species has a larger first ionization energy? Y. You can go ahead and pause if you want. You have to locate these on the periodic table. I'm going to show you the answer in a moment. O has a larger first ionization energy. It has only 2 shells of electrons. S has 3 shells, so O's electrons are closer to the nucleus. They're held more tightly. More energy is needed to remove them. Oops. S versus P. Locate those on the periodic table. Pause if you want. And we want to know which one has a larger first ionization energy. All right, here's the answer. Pause if you don't want to see it. S has a larger first ionization energy. S has 1 more proton than phosphorus. So left and right, you're looking at protons. If you have more protons, you have a higher effective nuclear charge. So phosphorus's nucleus has a weaker pull on phosphorus's outer electrons. So less energy is needed to remove an electron for phosphorus than from sulfur. Okay, you are going to do these on your own. I will show you the answers in a moment, so you should go ahead and pause. Make sure you paused. I'm about to put up the answers, so pause and make sure you read whether I'm looking for larger or smaller. And here are your answers. Check them out. Last topic du jour, last topic of the day, exceptions for ionization energy. I want you to notice something. If we look right here, we've got some exceptions, left to right exceptions happen. So the general trend was when we go to the right, ionization energy increases. However, beryllium boron, notice we go 899 to 801. That is not an increase, it's a decrease. Same thing right here. 738 versus 578, we've got a decrease instead of what we would expect, an increase. That is this one right here. 2s2 versus 2s2, 2p1, or 3s2 versus 3s2, 3p1. What's going on here? How do we explain this? And the idea is p electrons that are in the same shell as s electrons have more energy. Those p electrons have more energy, so it takes less energy to remove an electron that the electron itself has more energy. Remember our orbital diagrams? Those two p electrons are higher than the two s electrons in the orbital diagrams, meaning the two p electrons literally they have more energy, so it takes less energy to remove them from the atom. Now we have another exception. Okay, this time I want you to look, oh dear, I hate when that happens. Not going well today. Okay, we're going to look right here, this right here. So this exception is 2p3 versus 2p4, or 3p3 versus 3p4. So here we go. Nitrogen to oxygen. The general trend was that ionization energy should increase, but lo and behold, 1314 is not larger than 1402. 1000 is not larger than 1012. So our general trends are not holding up when we go from this p3, 3p electrons, to p4, 4p electrons. And let's figure out why this one's happening. And you have to look at orbital diagrams to understand this. And if you want to look at it, try to figure it out yourself, you can, but you should pause. Okay. For nitrogen, we've got 3 lone electrons. For oxygen, we've got paired electrons in that 2p sublevel. And here's what's happening. Those paired electrons, they are repelling one another. So in oxygen, you're removing an electron from an orbital where the electrons are paired, and those electrons are repelling one another. It's just kind of like they're pushing each other a bit. And if 2 electrons are repelling each other, it makes it easier, takes less energy to pull off this electron from oxygen than it does to take any of these electrons from nitrogen. Okay, that is it for today. Here's your summary. Sorry, I said that's it, and then I put one more little thing in here. Here's our summary of everything you learned today. Periodic table as we go up. Don't worry about Z effective. Let's just cross this one out. For up and down, what we care about up and down is the atomic radius and the ionization energy. Notice they have opposite trends. Left and right, ionization energy goes up, atomic radius goes down, Z effective increase because protons increase. And that is it.